50 years ago, Apollo 17 astronauts manually recovered orange soil samples from the moon. Now, EGB320 are seeking to return for more extensive mineral mapping in what could be a trillion-dollar industry. The rover needs to navigate obstacles, identify, collect, and deliver samples, remove the risk to life of manned operations, traverse unknown and complicated terrain, perform duties within a limited time window, and fit within the delivery vehicle. The rovers need to be highly integrated, cost-effective, and capable for commercial viability. We have developed our prototype orange sample collection and retrieval rover, Oscar, using an agile approach, simultaneously developing navigation, software, hardware, and manufacturing.
Hi, I'm Sean Hansen, and I'm responsible for the vision system of the lunar rover. The vision system is responsible for the rover knowing where objects in the environment are in the area in front of it. It does this by taking a raw image from the environment using the Raspberry Pi camera and then segmenting it based on the color of each object. It then draws a bounding box around each object in the frame. The vision system also calculates the range and bearing of each object with respect to the robot. It calculates the range of objects using a function obtained using regression to ensure accuracy. The vision system is also capable of identifying walls and the distance to them.
Hello, my name is Caleb Glasinga and I'm responsible for the mobility system of Oscar. The robot is driven through a pair of 298-to-1 geared motors positioned at the rear that drive a set of treads. The motors are powered from the battery through a PCB that cuts down on wiring and connects a voltage regulator to the Pi and other electrical components. The chassis is integrated closely with collection due to the constrained motion collection system design. The mobility program takes an input of rotational and forward velocity and outputs PWM to the motors through the DF robot motor driver. The robot is capable of ascending a slope of 15 degrees with up to 1.5 kilograms weight and can drive as slow as 20 millimeters per second.
Hi, I'm Dave, and I'm responsible for the collection system of Oscar. The collection system features a two-arm constrained motion path that matches the trajectory of a flipped rock. It uses a single servo to achieve both rock opening and sample collection, and features interchangeable tool heads and the ability to flip rocks of up to 800 grams. It carries the sample more than 10 millimeters above the ground to prevent sample contamination, and utilizes a brake beam for accurate rock flipping and a limit switch to report the sample bay collection status navigation. Finally, it features a controlled release of the sample to prevent it rolling away.
Hi, my name's Mason and I'm in charge of making sure the rover knows where it needs to go. One important part of this is making sure that it can avoid these obstacles and line up with the samples. It does this by creating a map of areas that it should and shouldn't drive to. It'll be drawn towards whatever it's seeking at the time, and it will be pushed away from other objects. Now, all of this is pointless if the rover can't ascend the lander and stop in the middle. It knows when it's on top by checking when it isn't tilted at all, measured by its onboard accelerometer. We were also able to cleverly use this equipment to tell when the rover itself has been overturned and requires assistance to right itself. At the start of our simulated mission, we exit the lander and attempt to collect a sample represented by an orange ball. If the brake beam sensor is not triggered, the rover will back up and attempt to collect the sample again. Once we detect that the sample is collected, the rover will attempt to return to the lander represented by a yellow podium. And it will attempt to ascend the lander until it's on top, and then it will deposit the sample. After depositing, the rover will exit the lander and then attempt to search for a rock, represented by a blue cube, because we have identified that samples could be hidden under the rocks on a real lunar surface. The rover will attempt to flip the rock by moving its collection arm, and if it fails to flip the rock, it will attempt to flip it again. Once the rock has been flipped, the rover will collect the sample hidden underneath and return it to the lander. Finally, the rover will attempt to find another sample out in the open. And if it doesn't find the sample while it is searching, it will bypass the closest obstacle and then search again. Once 3 samples have been collected, we deem this a successful mission. Please direct all expressions of interest and sales inquiries to EGB320.